Swayam Prabha. Digital India. Educated India.
Hello students. In today's lecture, I am going to use the concepts of thermodynamics in open systems that I have already developed to understand the problem of phase equilibrium. Now, if I remind you of the different situations that we can come across when we are working with the thermodynamics of open systems, the first example that we have seen already is the mixing of ideal gases. Now, using this example, I showed you how a binary mixture of two ideal gases, shown here in terms of the blue balls and the orange balls, I can have them being transferred from one region of the box to the entire box made available to them during the mixing process. So the same thing happens. Initially, the blue balls were located only on the left-hand side of the big box, and therefore, as a result of mixing, I would say that now they have gone to all the places all throughout the big box. And similarly, the same thing happened to the orange box, where instead of being concentrated in one region, that is the right hand side of the box, now they are spread all over the box. And the other example that I would like to cite here in order to discuss thermodynamics of open systems is phase equilibrium. Now, what is phase equilibrium? Let us say that you have a pure substance contained within this box as shown. Now, at a given temperature and pressure, this pure substance may not be stable as a single phase. Therefore, when we prepare this pure substance at a given temperature and pressure, you will see that spontaneously, in addition to the existing phase, another phase will appear in your system. Now, what will happen? If you continue under identical condition, then this new phase will start growing in size. So, if it is a liquid to vapor, initially you have a box full of liquid, then a small bubble of the gas is formed, and this bubble will start increasing in size, and there will be other bubbles getting produced and growing in size, so that eventually what you have is, at equilibrium, the liquid and the gaseous phase coexisting in equilibrium under the given condition of temperature and pressure. Now, if I am studying this coexistence of liquid and the gas phases, in that case you understand that in going from this state to this state, I need to supply the latent heat of vaporization, and then what I will have is more and more matter will be transferred from the liquid phase to the gas phase, thereby increasing the volume of the gas phase and decreasing the volume of the liquid phase. And therefore, when a new equilibrium state is reached, I will have both the liquid and the gas phase under the given condition of temperature and pressure coexisting in equilibrium, such that there is no more apparent transfer of matter from the liquid phase to the gas phase or vice versa. In that case, I will say, under the given condition of temperature and pressure, a phase equilibrium is established between the two phases. So now you see the kind of generalization that I am trying to put forward here. In my first example, I did not have any such phase equilibrium. The concept of phase equilibrium was not there. That was because my blue component and the orange component of my gas mixture, they were stable as in their respective gas phase all throughout the change in state. Now, when I'm studying the phase equilibrium, I have this additional complication that whatever material my system is made up of, under the given condition of temperature and pressure, it's not stable in a single phase. And now I have at least two phases which can be stable at that given condition, and therefore by appropriately managing the experimental condition, supplying the latent heat if it is required, I will establish an equilibrium where certain amount of one phase will coexist with certain amount of another phase, which is also possible for that system. The third example is again a very complicated one, and I'm talking about the chemical reaction equilibrium. So if I give you a pictorial representation of the situation that I'm thinking of the blue reactant and the orange reactant. Initially, they were not mixed with each other. When I induce a change in state, then what I will find that not only the individual blue and orange molecules are spreading out all throughout the box, but there is something else that is happening. In the example that I have given to you, you see that some of the blue molecules are now missing in the final mixture, and also some of the orange molecules are missing in the final mixture. Now, instead, what has happened is I have created two new species over here. So, they are the products of the chemical reaction, and therefore, when a chemical reaction equilibrium is established, I understand that my final mixture is going to be very different from the initial mixture in terms of the fact that the blue components would have undergone a change in number, the orange components would have undergone a change in number, and the pink components, which were not there at all to start with, have now become a non-zero number. Therefore, it is very important to understand that in all these very complicated situations, we are actually looking at the transfer of matter. While in the mixing of ideal gases, I was looking at transfer of the molecules of the gas, blue gas and the orange gas, from one region of the box to the other. While a phase equilibrium was getting established, I was talking about transfer of matter from one phase of the substance to the other. And finally, when I'm talking about the chemical reaction equilibrium, then not only my individual molecules move from one region of space to the other, but also I see that there is a changeover from one or more chemical identities of the molecules involved. But once again, as you see that the individual components, their number is not remaining the same as I pass from this initial state to the final state. And therefore, it is now clear to us that we can treat all these three examples under one set of generalized condition, that is the thermodynamics of open system, which allows transfer of matter. And here we are talking about transfer of matter from one region to the other, or from one phase to the other, or from one chemical identity to the other. Now, to start our discussion on phase equilibrium, we need to understand first the question of phase stability. So the point that I would like to explain here is that for a pure substance, the stability of that substance in a given phase is obviously a function of temperature and pressure. So if I now use the formalism of thermodynamics that I have already developed, then can I connect the stability of phases of a pure substance to the concept, for instance, of the chemical potential? And the second part in the discussion would be, if I now understand the stability of phases, can I think of the equilibrium between two or more phases as a function of temperature and pressure? So let us first take up this topic and try to connect it to the formalism of thermodynamics of open systems in terms of chemical potential. So when I talk about the chemical potential and phase equilibrium, I know that I am talking about the equilibrium state of a system as defined by a given temperature and pressure. And if I have a pure substance, then a great simplification occurs, because then I can say that the chemical potential at this temperature and pressure is nothing but the molar Gibbs free energy of the system at the same temperature and pressure. And therefore, this is nothing but, once again, the total Gibbs free energy of the system. If it is comprised of capital N particles, then G by N gives me the molar Gibbs free energy. Now let me consider a system for which there are two phases, alpha and beta, at equilibrium with each other at a given temperature T and pressure P. In that case, I can say that mu alpha Tp must be equal to mu beta Tp. So it basically says that look at the phase alpha. The substance at a given temperature T and P, when it is present in the phase alpha, its chemical potential is mu alpha. When it is present in the phase beta, in that case, under the same condition of temperature and pressure, its chemical potential is mu beta. Therefore, for the two phases to be at equilibrium with each other, I must be having mu alpha equal to mu beta. And therefore, I conclude that at equilibrium, the chemical potential of a substance must be the same throughout the sample, regardless of how many phases are present. If I had some other pure substance where I could have alpha, beta and the gamma phases coexisting in equilibrium at temperature T and P, then what would be the condition of equilibrium, phase equilibrium between the three phases alpha, beta and gamma? I must be able to write that mu alpha, that should be equal to mu beta, that must be equal to mu gamma under the given conditions of temperature and pressure. Now, if I go ahead and think of the chemical potential of the ith component in a mixture, then I know that I can always define the chemical potential of the ith component at a given temperature and pressure as the derivative of G, that is the Gibbs free energy, with respect to Ni, where I am using Ni as the number of particles of the ith component present. And in this case, many times for convenience, instead of the number of particles, we use the number of moles. We have seen this definition before. And now let us have a pictorial representation of what I mean by a phase equilibrium in a mixture like this. So let me consider a binary mixture of these orange balls and these red triangles. So my component A and B. The mixture at a given temperature and pressure, it can exist in two phases. One is the phase alpha, another is the phase beta. So the lower portion of this box contains the phase beta and upper portion of this box contains the phase alpha. Then the chemical potential of the ith component in this mixture must be obeying the following relationship. So let me choose the ith component, either the orange one or the red triangle, and let me focus on that. So let me say that I am looking at the red triangles in this binary mixture. Okay, so that is my I. So it is present in both alpha phase as here and also in the beta phase as shown here. It is, and both the phases are present at a given temperature T and P. Then what is the condition that the phases alpha and beta are in equilibrium with each other at this given temperature and pressure? I must be having mu I in the alpha phase equal to mu I in the beta phase for all i's that make up this mixture. Therefore, this relation must be valid not only for the red triangles, but it should also be valid for the orange balls. Therefore, the statement is, at equilibrium, the chemical potential of any substance is the same throughout the sample, regardless of how many phases and how many components are present. This gives us some idea about how we define phase equilibrium in terms of chemical potential. Now, let us examine the question of phase stability in a pure substance. And for this purpose, I would like to remind you that we have derived this relation that d mu is equal to minus molar entropy into dt plus molar volume into dp for any given substance. And I understand that this equation expresses mu as a function of temperature and pressure. And therefore, I understand that I can vary temperature keeping pressure constant, or else I can vary pressure keeping temperature constant. And my question is, can I now examine the stability of different phases of a pure substance when I vary temperature or pressure keeping the other quantity constant? So the first thing that we are going to discuss here is the temperature dependence of phase stability. And for this purpose, I am going to show you how chemical potential varies as a function of temperature if I am making these plots at a given pressure. So first, let me look at the behavior that I expect. I know from this equation that del mu del Tp is equal to minus Sm, where Sm is the molar entropy of the substance. So now it says that, well, if I am in a temperature range at a constant temperature such that only one phase is possible, then for a given phase of the substance, if I plot mu as a function of temperature, then different phases are going to have different slopes. Why is that so? That is because I know that the molar entropy of a solid phase of the substance is less than molar entropy of the liquid phase, and each of these values are much less than the molar entropy of the gas phase. Why is this so? That is simply because in the gas phase I have maximum disorder at the molecular level. In liquid, we have short range order but no long range order. Therefore, it is less disordered compared to the gas phase. While for the solids, I know that the underlying molecular picture has all the atoms or the molecules of the solid in periodic lattices, and therefore the solids have both short range as well as long range ordered structure. And therefore, I can very easily conclude that as I go from solid to liquid to gas, the disorder in the underlying molecular structure of the system increases, and correspondingly, if I think of their relative magnitudes of entropy, the solid is going to have the minimum value of entropy at a given temperature. Then the liquid will have a little higher value of entropy, and gas is going to have a much higher value of entropy. Now let me think of a temperature as shown by this line. So I am looking at a temperature where at this temperature, these are the values of mu solid, mu liquid, and mu gas is way up above there. Now, if I prepare the system at such a temperature, then what happens? If somehow I can prepare the solid, it will remain stable with its chemical potential at this value. But if I somehow supercool the liquid and prepare it here, then what do you expect will happen? With the slightest perturbation, this supercooled liquid will irreversibly freeze into the solid at that temperature. Why is that so? That is because I see here that the chemical potential of the liquid curve, which I have extended over here, the chemical potential of the liquid is higher than the chemical potential of the solid. And also, I have the chemical potential of the gas way above somewhere here. As a result, I make this note that over this range of temperature, where T is less than Tf, mu solid is minimum and mu gas is maximum. Therefore, somehow, even if I prepare the states supercooled gas or supercooled liquid, then they will be ready to undergo an irreversible transformation from the liquid or the gas phase to the solid. Why is that so? Because that process will then be associated with a decrease in chemical potential. Therefore, there will be transfer of matter from the less stable phases like liquid or gas, which are present at a higher chemical potential, to the phase where the chemical potential at this given temperature and pressure is minimum. Therefore, I can very easily understand by looking at this picture that if I am at the temperatures less than this temperature Tf, so that is along within this temperature range, I am going to have the solid state as the most stable phase because it has the least value of chemical potential, or in other words, it has the least value of the molar Gibbs free energy. Now, because of the varying magnitude of slope, this particular observation is happening. Now, have a look at this behavior of mu versus T. Now, for the solid, I have mu decreasing with temperature with the least negative curve. I have the liquid decreasing with temperature having the moderate negative curve, and the gas decreases most steeply in chemical potential because it has the largest negative value as the slope of the curve. Therefore, I understand that this is at the basis of why at this temperature range I have solid as having the lowest chemical potential. And therefore, I conclude that the solid phase is going to be most stable in this range of temperature at this given pressure. Now, if I look at what happens at the temperature where the solid and the liquid curves cross each other. These are two straight lines with different slopes. Both of them are decreasing, and therefore I understand that they may intersect at some point. So this is the point that I have highlighted over here. Now, what has happened over here? I see that here at T equal to Tf, mu solid is equal to mu liquid. Now, I understand that here the stability of the solid phase is equal to the stability of the liquid phase. So, both solid and liquid can coexist in equilibrium when at this given pressure T is equal to Tf. So, that is the melting point where I can expect to have a phase equilibrium between solid and liquid. Now, if I go ahead and look at the plot in the region where I am in between Tf and Tb at this temperature as highlighted in the figure. Now, because of the relative slopes of the three curves that I have shown here, I understand that in this temperature range, I have mu of the liquid having the minimum value, then comes the mu of solid, and then somewhere here comes the mu of gas. Therefore, I can say at temperatures Tf less than T less than Tb, all the temperatures T like this, I must be having mu liquid less than mu solid less than mu gas. So that tells me that in this range of temperature, my liquid state is going to be the most stable phase. And finally, when I look at the temperature T equal to Tb, this is the temperature when the value of mu liquid becomes equal to the value of mu gas, and therefore I can say that at this temperature the liquid and the gas are going to be equally stable and they can coexist in equilibrium with each other. Now, what happens if you are at a temperature in this range somewhere here? Now, by this temperature, the mu versus T plot of gas has ensured that the gas has the lowest value of mu. And therefore, following the same train of logic, we would say that this is where the gas phase is going to be most stable. So you can argue that if I can prepare something like a superheated liquid, it is possible experimentally to do that. If I do it, then at this temperature, I will be probably creating the system with a chemical potential equal to this value. Now, is it stable? The answer is no. That is because at this temperature, this is not the phase of this substance having the lowest chemical potential. Therefore, if I perturb the system even by an infinitesimal amount, the system will undergo an irreversible change in phase and go over to the gas phase, which is associated with a lowering of the chemical potential, and therefore the substance will undergo a transfer from the unstable liquid phase to the most stable gas phase. Therefore, under such condition, I would find that there will be no phase equilibrium. only one phase is going to be stable. So to summarize, we will look at this picture and tell you the following. We are looking at the phase stability of a pure substance. Why pure substance? We wanted to keep the description as simple as possible. Therefore, we have considered the pure substance. And in this pure substance, all we have done is we have looked at the variation of mu as a function of temperature for a given pressure. And then we find that yes, for a given range of pressure, if I identify a single value of mu in a single phase, which is the minimum under the given condition, only the system will be stable in a single phase. But if it so happens that for a given temperature, the mu values of two or more phases are equal to each other, then I would say that phase equilibrium is possible. Even if by adopting special experimental means, you create a superheated water or a superheated liquid or a supercooled liquid, in that case, what will happen is with the minimum perturbation, the system will spontaneously undergo a transition from the less stable phase to the most stable phase. And that is how we will get the supercooled liquid solidifying into the solid phase at low temperature, or a superheated liquid at a temperature beyond the boiling point immediately evaporating and getting converted into the gas irreversibly. But if I am at the melting temperature or the boiling temperature, it is under those conditions that I would see the phase equilibrium, because then the coexisting phases have equal chemical potential and the transfer of matter will not take place anymore, and I would say that the equilibrium has been achieved. Thank you.